Okay, in this video we're looking at complex numbers as vectors. Now, I probably have spoken about them on the complex plane before, and in this video we're essentially just going to formalize it. When you've got a complex number like this, 2 plus 3i, you can think of this as like an x and y coordinate. So if you've got a vector, it looks like that, or if you want to think of it as a point, it looks like that, with 2 as your x and 3 as your y coordinate. It's just that on your imaginary axis is your y-axis, and the real axis is the x-axis, and that's how we visualize this. Reason being, if we have our real numbers, like 0 and 1 and 2, and -1 and -2, we can chuck everything we want on here. We can put numbers like 0.5, we can put numbers like √2, we can even put numbers like pi over here, but there's nowhere where we can put square root of -1. That does not exist on the real number line, because if we want to have something squared equals -1, well, it's not negative, because negative squared is positive, and it's not positive, so that sort of rules out the negative and positive bits of the real number line. What we have to do instead is make this imaginary number line, bam, and then we know this thing here is called I sort of sits up here, and we'll label that with 1, 2, 3 to sort of mean I, 2i, and 3i. Then if you want combinations like 2 plus I, might be sitting up there, 2 in the real bit, 1 in the imaginary bit for I. Or if you like, 2 plus 3i is sitting up there, it's a bit higher. So we label this with the imaginary axis and we label that with the real axis. And that's sort of how this works. Imaginary numbers or complex numbers are actually 2D kind of objects, not 1D objects like we're used to with numbers. But it all works out well, and it turns out to have some really beautiful implications with coordinate geometry, which we'll see down the track. But at any point, in this video, we're just going to sort of be graphing and interpreting complex numbers on the complex plane. It's sometimes called the Argand diagram. That just means draw it on a grid. So z1 equals 3, that's the real bit. So you can think of x being 3, and y, which is the imaginary bit, is sort of just like nothing there. So z1 is going to be this point here. You can sort of draw it as a vector z1, just like that. z2 is going to be 4 plus 3i, so that sort of sits up in this space here. Here's z2. z3 is 5i, so that sits up here. z4 is -4 plus 2i, so that sort of sits there. z5 is -3 take I, so that sits there. And then z6 is -2i, so that sort of sits there. You can read off the real bits as your x coordinates and the imaginary bits as your y coordinates, if you like. Next, what we're going to do here is find these values using algebra and vectors. So what I've sort of got here is z1 equals 3 plus I, so I'm going to draw that straight in here. This is z1 here. Now z2 I'm going to draw head to tail, so the vector sort of goes up there. 1 take 4i, so across 1 down 4 brings us here. z2, and that's sort of head to tail there. And then if I want to look at z1 plus z2, it's going to be that vector there, which you can see goes across 4 and down 3. So it appears that z1 plus z2 is going to be, well, 3 take 4i. Now let's actually check. So that was geometric, just by sort of like having a look. But there's the algebraic version we can do. So z1 equals 3 plus I, z2 equals 1 take 4i, and if we want to add those together, z1 plus z2, the real bits 3 and 1 give you 4, imaginary bits 1 and -4 give you take 3i. And that is the algebraic bit, which is your writing down version, not by looking. Alright, next thing we're going to do, let's work out the next bit of our question, I suppose. So we're going to do z1 take z2. Now this is going to be a very similar idea to what we had originally. So there's z1, which sort of points out that way. Now we're going to do negative z2, which points in the other direction. You sort of imagine minus z2 equals -1 plus 4i. So it's going to step back 1 and up 4. Back 1, up 4. There we go. So this vector here is going to be z1 minus z2, which appears to go across 2 and up 5. So 2 plus 5i, and this is your geometric version. This is by looking. Algebraic version, so what we've got to do is we've got to step out z1 and z2 again. 3 plus I and 1 take 4i. And I'm instead going to be taking those away from each other. So that's z1 and that's z2. And this is going to be z1 take z2. So 3 take 1 gives us 2. I take -4i gives us +5i. because the -4, you got two negatives making a positive there. And we can see we get the same answer regardless.